Hey, you all, welcome back. This is lesson 22. We're going to start with this warm up in honor of Teacher Appreciation Week and Mother's Day coming up. Who is one person that you are thankful or grateful for? What has this person done that means so much to you, and how would you want to thank them? It doesn't have to be a teacher or a mom or mother figure, but that's kind of where this question was coming from. All right, so thank you guys for being here. Thanks for remembering our classroom expectations to be safe, responsible, respectful, prepared, and here. Remember, you're here for this lesson. If you were not in the Group A, so Tuesday live version, the virtual Wednesday lesson, or the Group B Thursday live lesson in person. Those are the days when we do our live lesson dependent on which group you're in. If you ever miss those, then you need to watch this right now. This week, we're talking about how mass is conserved in the chemical reaction. So kind of carrying over what we discussed last week with energy and applying it to this law of conservation of matter. There are 5 assignments this week. I hope that you had at least gotten a start on 57, 58, and 59 before coming here now. All 3 of those assignments are supposed to be done before we do this live lesson. There's 2 new assignments posted for after this lesson. One is the mental health check assignment this week, which is about self-care, and number 60, which is a Colorado FET guided form having you go through a simulation working on balancing chemical equations. So, skipping over this stuff to get started, what occurs during a chemical reaction? So, to review some things, we started off our discussions on chemical reactions by looking at collision theory, which is the idea that all molecules and particles are constantly in motion and they are constantly striking into each other and bouncing into each other. Now, I want you to try and remember what are the 2 things that must occur for those collisions to result in a productive reaction. Right. So hopefully you remembered that they have to hit each other with a sufficient amount of energy. They have to hit each other hard enough or fast enough, and they have to hit in the correct orientation or the correct direction. Now, when that happens, we're going to look for some evidence of a chemical change. We might see a temperature change like last week when we learned about exothermic and endothermic reactions, other energy being given off like light, color change that includes resting, or solids forming from liquids, which we call a precipitate. Bubbling and fizzing, which suggests the formation of a gas, is the one that we're going to focus on this week. Again, to visualize all of these for you. So there's lots of examples of chemical changes that we have now brainstormed and thought of, and we should feel comfortable with identifying if it is a physical or a chemical change. But with a chemical change, the important piece is that we are recognizing that a new substance is formed, a new molecule is formed. Whatever your reactants are that you're starting with, those particles, those atoms are rearranged to form something new in your products, as opposed to a physical change where we're just changing the outside appearance of something. So like baking a cake, we start with individual ingredients, individual reactants that all have their own look, feel, properties, etc. They undergo a chemical reaction that brings them together to form a whole new product, this cake. But the cake still does include each of these individual ingredients in it. Also, another great analogy is with the Legos that you saw in the video. If you start by building a Lego building or a structure, and then you take those exact same Legos and rearrange them to make something else, that's what's going on in a chemical reaction. So let's review and remember what is going on in this image here, or this GIF. So this is a bath bomb, obviously. Do we think this is a chemical or a physical change? So most of us should identify that this is a chemical change. Those bubbles being produced and the interaction that it's having in the water is not just physically changing it. So we want to dive into a little bit more about what's going on and what those bubbles exactly are. So I want you to think of what were some questions that you had about where these gas bubbles come from. As always, let me remind you, I don't know is not an answer. There is really no wrong answers besides I don't know. Great. So some of the questions we had is, where do those bubbles come from, or what could they be, or are they a result of a chemical reaction? All of these are great thoughts and great questions to have. So what we're going to do is try and figure out where exactly these bubbles are coming from. Were they in the bath bomb already to start with, or is it coming from something else? And what does that mean? So we should think about, let's think about this and kind of do some prep work and if and put this into two categories of where these bubbles could come from, this gas. All right. So first of all, what do you think we would see if we did a reaction and or we react our bath bomb and our water, and what would it have to look like if the gas was coming is brand new stuff that wasn't there before? So if we were, again, we're reacting this, let's even say inside of a plastic bag, a sealed plastic bag. What do you think would the black bag would look like if it's new, and what would happen to the mass? Right. So if it's something new that wasn't there to start, the mass of that bag, that water, and that bath bomb would have to increase because we would have added something new to it that wasn't there before. The bag might inflate, the bag might get bigger, the bag might look like there's more stuff in it because this, again, if this gas is something that's new that wasn't there before, it would have to have been open to allow it to come in and added to the overall mass, the weight. So now what would it look like if the gas is not something that's new? And specifically, I want you to think about what would happen to the mass, again, how much it weighs if I zipped up that Ziploc bag, and then what would happen to the mass if I left the top of the Ziploc bag open when we reacted our bath bomb and our water. So what we should think about here is in this closed system where it's ziplocked tight, the gas that's created would not be able to be released. So everything would be contained. And even though gas doesn't weigh much, it does have a mass. And so if it was able to leave and the mass didn't change, then that would the mass then wouldn't change in our closed system. If it was not new stuff and it was something that was already there to start, but just kind of or was reacted and released. If it was not new stuff and it was in an open system, however, that gas would be able to be released. And so that means that the mass of our reaction, of our water and our bath bomb and the products there would have to decrease because the gas would release and we wouldn't have that gas there. So what we're going to do is actually, we're going to view just one experiment. So you're going to watch this video that I'm going to post here in a second, and you're going to record data and observations in a notice and wonder chart about what happens. The notice and wonder chart has a closed and an open. The closed and open starting mass will be the exact same thing. In the video, it will do first, it'll tell you what the ending mass is, and then they'll open it up and they'll give you the ending mass of the open, okay? You're going to record that in this link here in a notice and wonder chart, okay? So again, opening up your notice and wonder chart, what we'll see is it'll have you make a copy. Just click it once if it's being a little slow. But what you're going to start by doing is making sure you put your name and the period of the class that you belong to. Then the second slide is going to have you make some predictions about what you think you're going to see. And then your charts that you're going to fill out will be next. So again, what do you think is going to happen? What is the mass going to be before and after? And then again, we have our closed demo, which is the first part of the video. And you'll record, she'll tell you the starting mass and she'll tell you the ending mass. Excuse me. And then the open demo, you'll use the exact same starting mass as you did for this one over here, but you'll get your ending mass after she opens up the reaction, okay? So by clicking on this link here, I want you to go watch this investigation video on your own right now. Great, so what you should have seen in this video, it should have looked something like this, where you're watching the scientist work and do this investigation. Well, clearly not this, because this is our advertisement. But once this is able to let us click through, you will have been able to watch this experiment, okay? So again, at the beginning, she talks you through and gives you the beginning mass, right, with everything in it. And then at the end, there's two masses that you'll record, the one before and then the one as she popped this open and released the gas that was created. So your last piece of what you're doing here is you're making sure to fill out the notice and wonder chart at the end of your slides. So the very last one is taking a second to compare and see what you saw in the closed demo and the open demo and write down some notice and wonders. So what you probably saw, or what you saw in that video, is that when the starting mass of the closed demo and the open demo was about around 141.8. In the closed demo, after the reaction occurred, she went and she measured the weight again, and she saw that in the closed demo, when the cap was on, that the mass had not changed at all. It still weighed 141.8, right? There we can see it again. But then when she opened up the tab and took that off and let the air release out, it was 141.2. So there was a change in 0.6 in the open demo. That's what we ended up seeing. So what does that mean? What the heck does that mean about what we saw? Well, so what that tells us is that in a closed reaction, like we saw, is that the mass of the reactants and the products are going to equal the same thing. And that makes sense, again, if we go back to our Lego explanation, where whatever you have to start is going to be there at the end. It's just rearranged into something new. In our open reaction, the gas was able to be released, and we were actually able to see how much gas was created. The 0.6 grams, that is exactly how, or 0.06 grams is how much was released. And so this is a really nice explanation to give us an idea of where is this gas coming from. So let's see, which of these claims do you think best describes where is our gas coming from? So claim 3 is definitely not right because it did not come from some other matter. Our mass did not increase as the reaction occurred. So it could not have been coming from somewhere else. It had to be something that was already there. Claim 1 seems right at first, but this is describing more of a physical change, that the gas was already created and it was just kind of released. That's not what we saw happen. We saw a combination or rearrangement of matter in there as in the form of a chemical reaction. So our correct claim would be claim 2. So our next question, and that we're going to be exploring next in next week's lesson, is what exactly do you think is in the bath bomb that's creating these bubbles, and how do you think we can find it out? So what are your thoughts? Cool. Well, the good news is that if we're able to figure out or look at what ingredients we have, it will be really easy for us to figure out what exactly the gas might be because of this law of conservation of matter. Because we know whatever this product is, it has to have come from the reactants in some way. And so we're going to continue thinking of this law of conservation of matter, not only this week but next week. You're going to practice your understanding of the law of conservation of matter by looking at chemical equations and determining if they're balanced or not. If, again, the idea is if whatever you have at the beginning has to be there at the end, a chemical equation is going to be what we call balanced. So after practicing the assignment earlier this week where we were counting how many each atom are in a molecule, we're going to put that to practice to see if the number of each element on the reactants and the product side are equal to each other or not. All right, so that's kind of what you're going to be working on and practicing with the Colorado FET this week. Don't worry, I'll give you some more practice next week. The Colorado FET is number 60, and besides your mental health check, that is the last assignment of the week. So let's finish with this. What was the most important thing that you learned from today's lesson? Again, nothing or I don't know are not answers. I will pretty much accept anything else though. All right. Thank you guys and have a great day. I will see you next week. Keep working on this week's assignments and remember that you can always go back and do any of your old missing or make up assignments as well to continue to improve your grade. Thanks and have a great day. Bye.